Alright, so quick review on circular motion, looking at the vertical plane. So all the equations of motion, circular motion, relate to this, but what we do have is the addition of other forces taking part, particularly the gravitational force. So we've really got two different scenarios that can take place here. We've either got the roller coaster or string scenario. Both these scenarios are pretty much identical in the way that you work. So at the bottom of the circle, you've either got your roller coaster cart, you've got mg that way, you've got your normal reaction that way, or you have mg that way and tension that way. The net force that's causing the circular motion is your centripetal force. So the overall force, the net force, the difference between the tension and the weight, will give you your resultant force. So your net force is your centripetal force, but at the same time we can say that that must be equivalent to the upward force, that's the one that's pointing towards the center, minus the one pointing away from the center. So it's either T minus mg, or you could have N minus mg, depending on which scenario you're looking at. Does that make sense? So it's analysis, it's a force analysis to start with. Okay, find my net force, and then I know that my net force, mv squared on r, is my net force, but that's equal to my normal reaction force or my tension force minus the weight force. Because it's got to overcome the weight force, this much must be greater than the weight force. So it's where it always feels when you're swinging something in a circle, it always feels much like it's pulling down on you much harder in your hand when it's at the bottom than as opposed to the top, or while it feels like you're being squashed down into the bottom of the car at the bottom of the rotation. The other scenario that you've got to look at, we've only got to consider the bottom of the circle or the top of the circle. The other scenario is at the top. So we've either got, whoops, a crazy cart, and in this case the weight force is acting down and the normal reaction force is acting down, or tension is acting down and the weight force is acting down. So we treat these two similarly. So in this case the net force is equal to the normal reaction force plus the weight force. Both of them act towards the center, or if you've got the string, it's the tension plus the weight force. In this case the tension is going to be relatively small because the weight force is supplying a fair amount of the centripetal force. So if we've got constant speed around here, then the tension is going to be strong when the weight's at the bottom. Tension is going to be relatively small when it's at the top because the weight component provides a large amount of the net force. Okay, so if we, going back to the top, if we rearrange that, the normal reaction force or the tension force would be equal to the centripetal force, mv squared on r, plus mg at the top. If we're at the bottom, normal reaction force or the tension force is equal to, so mv squared on r, mv squared on r, take mg. It's going to be smaller, going to be less than the actual net force. And then it's this scenario here where they're going to ask you, what's the minimum velocity required to make the loop? So at minimum velocity, t equals 0 or n equals 0, whichever scenario you're working on, the process is the same. And so therefore, mv squared on r must equal the weight force. It's solely the weight force applying the centripetal force at that very instant. So rearranging, divide by m, multiply by r, take the square root, v equals square root of rg. That can be on your cheat sheet as a little reference. Minimum for roller coaster or string, v equals square root of rg. The other scenario that comes up will be car in dip / over the hill. You'll notice if a car's going through a dip, it will be exactly the same as it is for the bottom of the roller coaster. So in all of the scenarios at the base, it's always the normal reaction force up, the weight force down, or the tension up and the weight force down. That's the same and identical for all three possibilities. So it's really only when we're going over the hill that there's a difference. So if we actually draw that in, we've got our car going over the hill. Here we've got a weight force down, but the variation comes when we've got a normal reaction force that's pointing up. Okay, at the top on the other two scenarios, all of the forces were providing centripetal force. In this case, it's only the weight force. Now, where's my pen? Over there. N must be less than mg, because F net must equal mg, our weight force, minus the normal reaction force. If there's to be a centripetal force towards the center, if we have a centripetal force acting down here, the weight force has to be greater than n, otherwise the net force points out. Or if there's weight is equal to the normal reaction force, there's no centripetal force. It's not going to continue in that circular path. Does that make sense? Yep. Okay, so in this scenario, you've got mv squared on r would equal mg minus n. And this is where the variation to the minimum velocity question comes in. Here we've got the maximum velocity to go over the hill. If they exceed this velocity, or at the point where there is no normal reaction force, exceeding this velocity means that the car then gets airborne. So we need, what we're after is the V where n would first equal 0. At the point that n equals 0, that will give us our velocity. So we'd have mv squared on r equals mg. Divide by m, multiply by r, take the square root. We've got v equals root rg again. Same equation, except we're now finding the maximum velocity before we get airborne. So the principle's exactly the same. It's just the scenarios, the reverse of when it's underneath the tracks, and what's the minimum velocity before it will go round. Here we're saying what's the maximum velocity. If we exceed that velocity, we no longer take that circular path. Instead of following right along the edge, if v is greater than v max that we'd calculated, then we actually get airborne. And then we follow gravity back to the ground for continuing on. Alright, does that make sense? Does that help distinguish between them? Awesome.